Good morning, everyone, and welcome to the third session of the first day of the Energy Machine Learning Symposium. Today we have Dr. Carrie Loudon and Dr. Jay Chi. They're going to be presenting on a topic that has broad interest to exploration and field development, AI-based fault detection. So Dr. Jay Chi received a PhD in geophysics from the University of Oklahoma-Norman in 2017, and he was a postdoctoral research associate at the University of Oklahoma from 2017 to 2020. He's currently a research geophysicist at Geophysical Insights, where he's working on machine learning-based fault detection, seismic facies analysis, pattern recognition, image processing, and seismic attribute development. Dr. Carrie Loudon holds a PhD in geophysics from the University of Minnesota and a BS in geology from the University of Wisconsin, Eau Claire. She has worked as a senior geophysical consultant with Geophysical Insights since 2017, applying the Paradise Machine Learning Workbench. Her prior roles include Vice President of Consulting Services and Microseismic Technology for Global Geophysical Services. Carrie was also with Schlumberger for 17 years in technical, management, and sales roles. Her work with Schlumberger included offices in Alaska, Aberdeen, Scotland, Houston, Texas, Denver, Colorado, and Reading, England. Carolyn spent the first 5 years after graduate school with ARCO Alaska in the exploration team as a seismic interpreter. We welcome Carrie Loudon and Jay Chi.
Good morning, good afternoon, good evening. Thanks for joining us today. I'm Jie Qi from Geophysical Insight. So today we will present a combined deep learning and unsupervised machine learning fault detection workflow. So in the first section, we will briefly introduce the AI fault detection using 3D convolutional neural network, which is a deep learning method. And traditional fault detection method is a time-consuming exercise based on hand-picking a suite of fault sticks on a coarse grid of seismic line, followed by passing surfaces between the sticks to form a fault surfaces. Seismic edge detection attributes such as coherence, variance, automated fault extraction, fault likelihood has been widely used to highlight faults on 3D seismic data for over 3 decades. Edge detection attributes can highlight the discontinuity surfaces, but can also generate some incoherent random noise and coherent random noise. So stratigraphic edge and seismic noise also give rise to this discontinuity in 3D seismic data. In recent years, machine learning and deep learning application to fault detection can be often seen in the recent publication. CNN, convolutional neural network, and advanced method rather than conventional seismic attributes has been proved its successful implementation in 3D fault detection. The result of CNN can further be applied to an unsupervised machine learning method, such as self-organizing maps to create the geobodies of the fault, then to finally create the fault surfaces. So we think that currently the best method is a combined AI method of the deep learning method and the supervised or unsupervised machine learning methods. Here are listed some challenges from the traditional method, which is the manual interpretation is extremely time-consuming. And seismic attributes-based method highlights faults, incoherent noise, and stratigraphic discontinuities. Image processing-based method often require high-resolution based map, which is the seismic attributes, and also have high computational cost. And deep learning can well address those challenges by the required less or non-manual work in the deep learning method. And deep learning method only classify data into 2 classes, faults or others. And deep learning methods spend more cost on training, but the actual application cost is lower than other methods. This imaging showing the general workflow of a deep learning-based convolutional neural network model that to apply to seismic interpretation. So this workflow can be divided into 2 steps. First step is training step, and the second step is classification step. So since the scene is a supervised learning method, so in training step, we need to create the training label and training data, which used to train the scene model. So the key part of the CNN deep learning workflow is this part of the convolution, which extract the feature from the training data and generate the feature map that we'll use to training the CNN model. So this training step may take several steps or several iterations. So once the CNN model has been well trained, we will apply the CNN model to classification step. In classification, we only need to input the application data, and it will go through the same steps and generate the label of the application data. So in fault detection, this label of the application data will be fault probability, which corresponding to this application data. This image is showing the main menu of Paradise software, which is a machine learning part here, which including PCA, SOM, jailbody generation, deep learning fishes, deep learning fault detection. So here we just focus on the deep learning fault detection. By clicking this button, it will pop up a window to ask you to select which model you would like to use. So here we introduce two models. One is a fault conservative model, one is a fault aggressive model. So fault conservative model is used to detect the major fault and which generate the less false positives. So in fault detection, false positive is kind of incoherent noise or other stratigraphic edges such as the channel edges, salt edges, or cluster collapse feature edges. So this conservative model that can be applied to data with either a high signal noise ratio. The second model is aggressive model, which used to detect most of the faults, maybe create a more false positive. So we only suggest to apply this model to data with high signal noise ratio. So all the same model in Paradise software has been pre-trained by the 3D synthetic data, which require no manual effort by the GL scientist. So our model can classify data into two classes, only fault or others. And high cost on training of the same model has been done by us. So the actual application cost is ultimately lower. So here we're just showing the two synthetic fault model examples. So one is here and other one is right here. So we can control some parameter to set up the fault and the reflectors and also changing the noise level of the different synthetic volumes. So in training our CNN model, we are generating more than 5,000 synthetic training model to cover the different fault parameter and different fault displacement or different reflected noise. So with those information, we were trying to make our CNN model to be sensitive to the different kind of discontinuity in which corresponding to the real applications. So one advantage using the 3D synthetic model is that we can remove the interpreter's bias by manually picking those faults. So since this is a synthetic fault label, so it can accurately address all the discontinuity, including those can be interpreted by interpreter or those cannot be picked by interpreter, such as this one like in the corner, this one right here, and some fault which has a very low displacement can also be well addressed in the 3D synthetic volumes. These two imaging is showing our two attributes that I used for the fault detection. One is the fault deep magnitude, one is the fault deep azimuth. So know that we define the fault deep magnitude is from 0 to 90 degree. The 90 degree means the vertical feature, 0 degree means the horizontal feature. Azimuth is using the cyclic color bar to represent all the fault. So based on the CNN Meister, we can build a Paradise deep learning based fault detection software, which including 4 steps. The first step is seismic data preconditioning. We apply conventional seismic data preconditioning to remove some random noise and incoherent noise and sharpening the discontinuity in seismic data. And in the second step, just the application of CNN model to generate the fault probability cube. We use a deep learning method which performs well on fault detection without any human-computer interactive work. And in the third step, we will further enhance the seeing result by applying image processing techniques to sharpening the fault and other discontinuities that cut reflectors. And in last step, we will compute the fault orientation attributes that will be used for the subsequent automatic fault extraction and the fault geobody generation. So here we will show two examples to indicate that how our Paradise deep learning based on fault detection software works for the different kind of fault. So this is our first example, the DJ basin, which had a normal and reverse fault. So first, we would like to apply our first step, seismic data preconditioning. The left vertical imaging here is showing the original seismic data. And the middle one is showing the PC filter seismic data, which is we apply the 3D structure-only filtering to reject some random noise, which is showing the third column here, and some incoherent noise. So note that our seismic data preconditioning works well on to removing those incoherent noise, which is right here, and also sharpening the discontinuity compared to the original seismic data. So next, we apply our seeing model to create the seeing fault probability model, which is showing on here. So note that the seeing doing well on the fault detection, it can picking those faults which cannot be clearly seen by the human eye here, and also right here. So seeing works well, but however, we can still see some false positives, and also the fault looks a little bit thicker on the original seeing result. So that's why we would like to apply the fault imaging post-processing, which is the third step on this Paradise workflow. And the middle one is showing the seeing result after the post-processing. So compare these two, note that the false positive has been significantly suppressed, and also the fault resolution has been improved compared to this original seeing result. Then we co-render them together to highlight those faults from the seismic data. So note that the fault can be well addressed and detect on this seismic data. And our last step is the fault attributes computation. So we first compute the deep magnitude, which is showing here. Note that from color bar, it's from 0 to 90 degree. And the second attributes, fault orientation azimuths, which is this one. Note that the azimuths indicate that the fault orientation. So the blue color indicate the fault oriented from like 0 to minus 30 degree. And the red or orange color indicate the fault that oriented to about 150 degree. And this is compared with the co-render of the seismic with the post-precise seeing result. This imaging is showing the different time slice, which is through 1.4 second, 1.5 second, and 1.6 second, which is right here. So note that all the fault can be well mapped here, and also the fault has very good resolution. And we can note that there are some the continuous fault right here on the 1.4 second, and on 1.5 and 1.6 second, there are many like small faults, which can hardly be interpreted by the geoscientists on this data set. So our second data example is Canning Basin, Australia, which is a shallow polygonal fault system around here, and a major fault system right here. So we apply the Paradise deep learning fault detection workflow to process this one. And this imaging is showing vertical slice through the original seismic data. This imaging is showing the same result after post-processing, goes through the same seismic inline. And this is the attribute, seismic attribute, this is fault attributes, which is azimuths. This one is fault deep. And also we're showing a cross example that highlights a lot of the small major fault right here in the middle and the polygonal fault system in this shallow area. So note that the manually interpretation on this data set is almost impossible. So there are a lot of small fault and also the major fault, polygonal fault on this data set. So I also would like to show this time slice. One is on the left through the polygonal fault system, and one is a little bit deeper, which goes through the major fault system. Looks like a Paradise software, we can very delineate those faults, no matter it's a small polygonal fault or those major fault. So my last slide right here is at least the computational cost of a different example based on the different data size, and also at least our computer configuration for the comparing. So note that most of the computational cost is on the conventional preconditioning step, our CS work and post-processing, and also combined with attributes computation step. So only takes a small computational cost. So overall, our Paradise deep learning based fault detection software is very efficient. So next, my colleague will show some live demos using the Paradise to process data for the fault detection.
Good morning. Thank you. Let me briefly introduce myself. My name's Carrie Loudon, and I'm a geophysicist with Geophysical Insights, and I spend most of my time helping clients use Paradise software and learning how to use our various machine learning tools. So I'm going to start with just an overview of the fault detection workflow. And this is the home screen in Paradise, and we have this very nice machine learning canvas that has all of our machine learning applications available. We'll return later to this one that I've highlighted some, but today we're going to look at how we run the fault detection in Paradise. So it's very simple. It's a left to right button selection that takes you through. And you can, in this case, I'm just going to use all the defaults using a whole volume. And really the important thing that I wanted to show is how flexible we've made this. So we've designed the software so that you don't have to be an expert on all of the preconditioning, like the structurally oriented filters. And but however, you can come in and open any of these menus and set your own choices. Likewise, this is the preconditioning. And you can set your number of iterations for both preconditioning and fault enhancement. And again, we have advanced parameters for the fault enhancement. And then you simply launch from there. So with that, that was just a very short demo. I'd like to go back and introduce a few slides to talk about combining the fault detection with an unsupervised classification via self-organizing maps. We're moving on to the next part of the agenda, which is called semi-supervised machine learning for fault detection. And what we're going to look at here is including our fault volumes as input to self-organizing maps. So what Jay showed was the output from the fault detection thought flow, which provides us with volumes of fault probability as well as fault dip and fault azimuth. And so we can take those volumes and put them into an unsupervised seismic classification, in this case a self-organizing map. And the advantages to utilizing SOM is that we can normalize these input volumes into discrete values that allow easy isolation and interrogation of the volumes to help visualize the faults. Multiple fault volumes from our different engines can be combined and yield a single fault volume for interpretation. We can also put these SOM volumes into Petrel or other interpretation packages as part of a fault extraction workflow. And neurons can also be converted into geobodies, and these can be filtered by size if required, and also used in a fault extraction workflow. So the steps in the workflow for SOM are to, again, start with your base amplitude volume, and from there you can create instantaneous attributes, which are helpful for stratigraphic analysis. And we take these instantaneous attributes and apply principal component analysis to help us select the most prominent attributes in our volume. And then we combine these with our fault attributes in the SOM, and then visualize those in 3D using our 2D color map in Paradise. So a quick explanation of self-organizing maps for those of you that may not be familiar with it. It's an unsupervised classification technique that takes 3D volume and survey space, and I'm going to make this just in the context of, say, 8 attributes that perhaps you're putting into the classification. So in survey space, each sample will have 8 values in the 3D survey, 1 for each attribute. Now SOM works in attribute space, so we take our subvolume of interest, usually it's the stratigraphic interval we're most interested in analyzing, and we put that into attribute space. So now we're going to be in 8-dimensional space. And the SOM process performs cooperative and competitive training to classify patterns and clusters in attribute space. So the SOM introduces neurons into attribute space, and through epochs of cooperative and competitive training, it classifies every sample in the volume in attribute space. Now the 64 patterns is selected by the user, and that is something that we commonly use, and it's going to show up in the 2D color maps that we're using. And this is an 8x8 SOM topology. So after classification, there's a nonlinear mapping technique that maps the clusters onto our 2D color map. And now each neuron on the color map represents a cluster of data points, and each data point retains its location in 3D survey space. So that's a very brief, condensed explanation of SOM. So now we're going to go back to these volumes that Jay showed in his fault detection section, and we're going to look at those in SOM. All right, so here we're looking at a cross line from the Canning 3D survey, and I like to start with this volume because I think it really illustrates the power of using a 3D classification and a 3D synthetic fault engine. This is a cross line through the volume, and I'm co-rendering the amplitude along with the fault probability from the enhanced fault detection workflow. And you can see we have different fault regimes up shallow. We've got some shallow faults. Through the middle here, we have a polygonal fault system. And then we get down into the kind of larger scale normal faults. And then going into the deeper section, we see the fault orientations change just a bit. So now I'm going to turn those off. And now we're looking at the same inline as a SOM classification. And what I've done here is create a classification volume of 8x8, and this has mapped everything into 64 neurons. Now within Paradise, we can take this 2D color map and we can change the colors to highlight specific neurons. So that's what we've done here. And I've used a grayscale for the stratigraphic features and turned the faults red so that they sort of pop. I think it's interesting to note, though, that we've picked up a lot of stratigraphy in the SOM. It's not just about the faults. So you could actually use this as a volume to help with your horizon interpretation as well. You can see some of the main packages here, the shallow faulted section, and then a whole change in character as you go down through the SOM. Now, what I'd like to illustrate with the color map is that we can go in and isolate individual neurons now and look at them. So that's a single neuron. You'll notice it's dominated by faults that are dipping in one direction. And as we look at the various faults, you can see their contribution to the entire SOM. And so I'm going to just quickly turn all of those off. So we selected those neurons, and then I'm going to invert the color map. And now you can see that you've isolated just the fault neurons. And so if you just want to look at faults, you can look at it this way. I'm going to turn on an inline to give you some idea, again, of the complexity of the fault system that we're looking at here. So here's the inline direction, and now you can start to see why this would be a very difficult manual interpretation, because we have faults in both the inline and crossline direction. So the last thing I'd like to show is a time slice that goes through the shallow fault section. And I'm going to turn on the background neurons again so that we can see the detail a little better. So now if we zoom in a little bit and look at the detail that we have in this SOM and the polygonal fault system, you can see the SOM has done a fantastic job, which actually originated with the original fault probability volume that we created. So it's done a good job, and now you could actually create a seismic volume that only contains the red neurons, and that would be just a fault probability volume with the neurons all connected up. So now with that, I'll move on to the second case study, which is Niobrara. Moving on to our second case study, this is on the Niobrara Formation, and using the seismic volumes that Jay showed earlier, we conducted a stratigraphic study back in 2018 before we had the fault, CNN faults. So I went and revisited that recently to see if we could combine our stratigraphic and fault results. So the Niobrara Formation is an unconventional target within the Denver Basin. There's a cartoon here showing roughly the depths to the various reservoirs, which we term A, B, and C here. It's within the Wattenberg field. Here's a look at where a seismic volume is in the state of Colorado, close to the city of Denver. This is a fractured chalk reservoir. So here is a two-way time structure for the 100 square miles that we're going to be looking at, and showing various structural elements along with some of the types of fracture systems that you would expect to see. So you can see structural highs on the west side, so north to the left. So we're coming up into the Rocky Mountains, and then it just dips off into the basin, but you can see evidence on the time structure map of the faults. The original amplitude data that we used in the SOMs was about a 60 millisecond window, and it's quite good quality amplitude data. The interval we analyzed was the top of the Niobrara, which is the top of the reservoir target, to the Greenhorn. And within that, we have these three chalk benches. I'm going to focus a little bit on the B bench because it was the initial first target for horizontal drilling. And it's this trough that you can see, peak, that you see behaves differently mechanically than, say, the top of the reservoir, which is very shaly and looks to be less brittle. So jumping right into SOM, we ran our normal PCA analysis and created an 8x8 SOM of instantaneous attributes, trying to bring out the stratigraphy. So you can see now this is our original amplitude data, and here's our 8x8 SOM from a few years ago. And our chalk reservoir, the best reservoir, is in this yellow package that you can see. So you can see the SOM really gave nice resolution to the bench that we were targeting. So recently we included the instantaneous attributes along with the three fault volumes, again, probability, dip, and azimuth. And then I created a color map that tried to somewhat mimic the original color map so that we could see the same stratigraphy. So again, you can see in the previous example, the canning, we were showing an entire seismic volume, so about 5 seconds of data. Here we're just showing 60 milliseconds of data, but again, you can see the fault classification has done a good job of isolating the faults into neurons via the SOM process. And now we'll go and just have a final look at these results in Paradise. So here you're seeing a two-way time structure map that's on the greenhorn, which if you remember is the base horizon we used in our SOM. And I've put the inline up that I just showed in the previous slide to kind of show you the SOM that we used. And what I want to do in this example is show you what we did with these SOM neurons, which was use our geobody tools from Paradise to take those isolated fault neurons and convert them into individual geobodies. So that's what I have now put up on the screen. So we essentially took that 3D volume of SOM and selected the neurons that corresponded to faults, and then created geobodies out of those, which is a geobody is simply a series of contiguous samples. So they're essentially connected samples. All right, so that takes you through the end of our tour through fault detection and self-organizing maps. So to wrap up, we'd just like to summarize that we've developed a fault detection workflow combining deep learning automated 3D CNN with state-of-the-art pre- and post-processing steps to produce high-quality fault probability volumes. The workflow can be fully automated or run serially in Paradise, and Geophysical Insights can also provide this as a service. We'd like a takeaway to be that the 3D synthetic fault model provides superior results over human interpretation in a fraction of the time, and I have a reference here you might consider that discusses 3D models versus models derived from real data. And interpreters can refine the results in a standard interpretation package. Self-organizing maps add additional value to the fault volumes by classifying faults into discrete neurons with known values. And the SOMs enhance the interpretation process and can be easily utilized to augment traditional interpretation. SOM utilizes attribute space to simultaneously classify suites of attributes into sample-based high-dimension clusters. And SOMs can effectively combine multiple structural and stratigraphic attributes into a single classification to aid in interpreting and visualizing multiple components of a given asset, be it a prospect or a producing field. In closing, I'd like to acknowledge the companies that provided data for these studies. The Denver-Julesburg Basin data was provided by Geophysical Pursuit and Fairfield Geotechnologies. The Canning Basin data is provided by Geoscience Australia, and the Opunake 3D data was provided by New Zealand Petroleum and Minerals. So thank you very much for your time and interest, and now we'd be happy to take some questions.
Okay, let's see here. In terms of questions, the first one, Carrie, I think we have for you. So what benefits have you seen in combining supervised fault detection with unsupervised classification methods?
Okay, thanks, Laura. That's a good question. And really, I'd say we didn't initially know that you could do this combination, but having the faults in the volume along with the SOM neurons that are often delineating stratigraphic features, it really helps with an understanding of a prospect or even a production area, because you can see compartmentalization and potentially you can see if target reservoir is of a limited area or whether it's contiguous. And also, even in an exploration setting, the SOMs can help bring out certain reflectors and aid in the horizon interpretation along with the fault interpretation as you're working through that process.
Okay, very good. The next one I think is for Jay here. Which is the minimum hardware requirement for the GPU to process these kinds of workflows?
Yes, thanks for asking that. So usually we have done many tests and we saw that so we at least we require a NVIDIA GPU that has 8 GB GPU memory. So that is a minimum hardware of GPU for the whole workflow.
One more thing. Somebody's asking, are there trial licenses available for Paradise to test?
I think the answer is yes.
Yeah.
Of course, and we would be happy to put you in touch with the appropriate or part of our organization to arrange that.
Sure thing. And by the way, for anybody presenting, or for those attending rather, if you'd like to get in touch with one of the speakers, please send me an email at admin@upstreamml.com with your contact information, and I'll be happy to pass that along to the speakers for them to contact you at their convenience. One other question here. For the DL model, I wonder what type of input data is used to train the model. Are they based on 2D pixel images or numerical seismic attributes?
I think that's Jay.
Yes. So yeah, that's a good question. Actually, we use a 3D workflow imaging, actually 3D workflow volumes for the training the seeing model. So that is not numeric seismic attribute, just the seismic amplitude data and the label that corresponding to the 3D workflow volume.
Okay. And then how can you handle complex faults such as reverse faults?
Since we're using the 3D synthetic volume for training our seeing model, that means we can simulate any kind of fault that we want to address those different structure. So we can only just input extra reverse fault on complex fault to our current model that to make our model to be sensitive to those complex fault and sensitive reverse fault.
Okay. Well, if there's no other questions, again, well, thank you guys very much for your presentation. And for those staying for Dr. Wei-Cheng Li's presentation from Aramco Americas, he'll be on shortly. You will go, tell you what, let me just pop on the screen here. So you'll close out of this presentation and then you'll go back to the live stream page when you first log into the site and open up Dr. Li's presentation from there. So thank you very much. We'll see you guys in about 20 minutes for Dr. Li.
Thank you.
Thanks. Bye.